seminar. We have Professor Alyosha Molnar from Cornell University today. Alyosha received his bachelor degree from Swarthmore College. Then he spent some time away from school working in places as diverse as a commercial tuna fishing boat and Connexat Systems. And then he went back to graduate school at UC Berkeley, where he received his PhD in electrical engineering. He then joined the faculty of Cornell University in 2007, where he's an assistant professor in the School of Electrical and Computer Engineering. Among other recognition, he has received the DARPA Young Faculty Award and the NSF Career Award. So, welcome to all.
Thank you. So, thank you for coming. Today I'll be talking about 3D imaging with CMOS against the pixels, and I will define all of those terms as we go. So, from there, don't worry. So, in this talk, I'll be combining three existing viewpoints on how to attack imaging in 3D imaging. So, one of those viewpoints is what's called light field imaging. I'll go into more depth in a minute, but the basic idea is to, rather than just capture the intensity of light at a plane, you actually capture both the intensity and also the incident angle. So you capture a richer description of the light, and that allows you to back out things like depth. Second viewpoint I'll take is the state that's sort of a bias coming from solid-state electronics, particularly integrated circuits. And so one of the goals of this work was to do whatever we did in the context of a standard CMOS process, which is to say in exactly the same manufacturing stream as in sort of computers or radios or any other form of chip. And the motivation there is basically humanity spent somewhere on the order of between $10 and $100 billion developing good manufacturing of chips. And what that has led us to a point where the actual chips themselves cost $1 or less. And so we've invested a massive amount of money in building tiny things. It makes sense to try to make use of that investment going forward to produce new interesting functions cheaply. And the last viewpoint I'll use is what I would describe as frequency domain image analysis. This is a well-known idea. It's what your brain does, in fact, is also what most compression algorithms do, which is to basically transform images through local, essentially Fourier transforms to get a sparser, sort of richer description of what you're seeing. So these three ideas will all come into play as we go. So I'll just briefly give you a sense of where we're going. I'll have some motivation. I'll discuss how to build an instance of pixel. I'll discuss how to use it to do 3D imaging. And then I'll discuss some other interesting things we can do with this information. So this is mostly just so you know where we are. So when you start looking at your watch, that sense. So I'll start with the motivation, just the low-cost 3D imaging. So when we started this, we were actually interested in sort of a replacement for a microscope. So we were thinking, instead of having a $100 or $1,000 microscope, what if we get a $1 CMOS chip? You know, for example, a fluidic pathway to image fluorescent cells, for example, in 3D. And the idea there is mostly to reduce costs by a couple orders of magnitude. And what we realized early on is that if we wanted to do this, if we wanted to get rid of the lens, the thing we needed to capture was incident angle. So intensity alone will tell you little. A single light source would make a very large blurred spot. But if we have incident angle, we can, for example, triangulate back to a much finer resolution. Once this idea generalizes to the case of the lens, if you have now if you do the same thing with the lens, if you're in focus, you don't need angle information. You have a nice, clear spatial image. It's great. If you move out of focus, now you have this problem. There's some ambiguity there. You blur your image, and you can't necessarily tell if you're closer or farther away in the general case. However, if you consider an angle, of course, there are very different scenarios. You can clearly distinguish the close case, which is that convergent, which is the far case is divergent. This is more of a conceptual idea. But just this realization that in general, if we could capture into an angle cheaply, we'd get a lot more information. And you can formulate this as a general light field problem, which is to say we capture information not only in the x, y dimensions, but also in the theta phi dimensions of each of those locations. So we can describe this in general as a planopic function. It's called a 4D planopic function, which is basically the intensity of the function of x, y, theta, and phi.
So if we were any,
yes.
So your sources and objects are incoherent.
Yes. That's right.
We're not looking at laser illumination.
No.
This kind of stuff.
That's absolutely right.
So just to say that.
Yes, that's absolutely right. So I'm interested either in if it's fluorescence, then it's active in a sense, but it's not. There's no structure to the light, and for a lot of the photography stuff, it's completely passive. It's just the ambient. That's right. So now an interesting point to make in this is that the optimal that I'll touch on again is the optimal sampling of planopic function actually depends on your focus. So if you're in focus, then you don't really need theta and phi. X, y is enough. But if you're out of focus, you start losing spatial information, things blur. But now there's actually more angular information present. So part of the game is to do a good job sampling this 4D function that's kind of aware of this trade-off that happens across different focal situations. So that's the light field side of things. Also, briefly, I realized CMOS is in my title. I usually speak to groups of people who do a lot of work with CMOS, so I don't have to define it. But there are geologists in the room, turns out. They don't know what CMOS is. So here's a quick two-slide introduction to why chips are cheap. So modern electronics chips are implemented in a series of layers. Hopefully many of you know this. And each of these layers is defined by a 2D mask. We basically just stack them up. So the idea is that if you can implement something, you can implement all electronics, it's just a series of 2D things that we stack up. And the more we stack, the more stuff we get, the more money we spend. But the name of the game is that. So for example, if I wanted to build a simple circuit, I would etch out my transistors, I'd add some gates, I'd add some contacts, layer down some metals, and so on. And the key point is each of these critical things are defined in terms of a layer, and then some 2D description with some critical dimensions. Now, the reason this is important in this era is that this is what makes them so cheap. These are tiny, but they're also very, very parallel. So we tend to spend a lot of money developing that layer stack. That's these days in the billions of dollars to develop a new layer stack. We spend a lot less money, but still a lot of money on the defining of those masks, because they're quite fine. But once we've done that, the cost of making a chip is tiny. If you want to mass produce chips, they're single dollars. It's basically, you can spend $1 billion to make it manufacturing, but you spend $1 to make it. If we're interested in individual components of those chips, which there are billions of, now we're looking at nanodollars, so to speak, of cost. So humanity has dumped an immense amount of money into doing this, but now that we have it, we have this incredible tool set. So the question is, how can we take advantage of it? So that's the second piece of this. How do I do light field imaging while taking full advantage of this massive investment we've already made to manufacture? Okay, so that takes us to the question of how do we measure angle information? So we're going to start with a very old idea developed by Henry Fox Talbot in the 1800s. We call it the Talbot effect. It's just this observation that if you take a periodic grating and you illuminate it with a plane wave, you get clear periodic diffraction patterns at specific depths below that, set by the Talbot depth defined here, which is just the pitch squared over the wave. So now, why is that good? Well, if you look at the Talbot effect and it's a simulation, and you change the incident angle, you look at the intensity at one of those critical depths, you'll see that the intensity pattern shifts laterally with incident angle. So we can rephrase our problem from detecting incident angle to detecting shifts in the Talbot pattern. Now, how do we do that in the context of sort of simple layers? We'll say, well, if we want to distinguish these two cases without necessarily having a fancy detector, what we can do is we can add a second grating in between, and now we get a simple situation where when the peaks of the Talbot pattern align with the lines of the grating that are blocked in line with the gaps that pass through. So we have a simple angle sensor that's just based on two diffraction gratings above the diode. Here's a numerical simulation of that to see what it does. You can see as we sweep incident angle, we get alternate pass and blocking scenarios, and so we get this very strong periodic function of incident angle. And we can model that with a simple function, so the response d0 is just proportional to the intensity coming in, the incident angle is sort of an envelope function of the whole thing, and then there are just a few critical parameters, which are the periodicity beta, we call it, which is just the peak-to-peak, essentially, and then m, the modulation depth, how close to zero we get. Okay, now this is, keep going. So now, it should already be obvious, but this is easy to implement in a standard CMOS backend because we can implement our gratings with metal layers. These metal layers are there for wiring to hook up transistors. So we, instead of using them as wires, we use them as gratings. It's free. You can set up both that way, and then we can get all of our sensor and amplification circuitry off the typical CMOS structures below. So all of the structures are already available for free. Somebody's already spent a lot of money developing this. We just draw it on a computer, send the file with a check to the appropriate company, and send us back to us. They don't even know they're building all of this stuff. As far as they know, they're building a computer. Okay, now there's a bit of an issue here, though. If I have just one of these alone, I can't actually tell anything about angle than I could before. And see this, we can say, well, say I measured this level of response. That could mean a couple things. It could mean I'm at one of these angles. Or it could mean things are dimmer, and I'm at that angle. And I have no way of knowing. So there's not enough information here to actually extract it into. However, if I also built a complementary structure that had the sort of antiphase angular response, then I could clearly distinguish these cases. Because now, for example, if these cases are the same, these are very different. And that's actually intensity invariant. The ratios is fixed. So how do I get that complementary structure? Well, I can just notice that But setting the sort of phase of this response is the relative alignment of our two gratings. So I build a second pixel next door, with a different shift, I get a different periodic response. And in fact, as soon as you get a cosine, yes, this is basically a cosine function we're seeing now. As soon as you get a cosine, the next thing you want is a sine. So we do an additional shift of half a period, and we get full sine and cosine description. So for this periodicity, we have all information in range. So we can model this. So there's our original model. There are the other 4 curves. They just have 90-degree phase shifts built into each other. And this is enough information both to extract intensity. If I just take the averages of complementary signals, for example, D0 and D1/2, here I get just the intensity out. Whereas if I do a little bit of trigonometry on the differences of them, I automatically extract the spin angle. So all the information is there. We have both the intensity information and the angle information, and they're essentially independent. Okay, and if you're a circuits person, I don't know if there's any real circuits nerds in the room. I'm a circuits nerd. In circuits nerd language, what we're saying is we would describe the intensity as the common mode signal, and the angle is being decoded in differential mode signals. So it's very easy to implement analog circuitry after this that encode the information that way. So we built it. This was our first test structure. It's rather large. It was built in a standard IBM CMOS process. What you can see is for our sort of standard tile, we have 4 phases, but we also have vertical and horizontal to get both elevation and azimuth. And there's the actual measured curves. They sure look a lot like our simulations. The only real difference is the envelope, and we're pretty sure that's a reflective effect on the surface. What can we do with it now? So how do we use it now that we've got our curves? So we started out with a very simple problem. We just built a small 8x8 array of these tiles. And we did a very simple experiment. We just stuck a light source physically about here, maybe more like here, and measured the response of all the photodiodes here. This is a map of that response. And what you can see is that there's quite a bit of heterogeneity within these blocks of 8. Well, the blocks of 8 are pretty similar. And that's basically because each of these sub-ones is a very different grading for them to be. Now, that alone is not at all informative, but from that you can compute angle, and you can generate, for example, a simple sort of map of what's the word for this? I lost it. Arrows. And you can, from that, you can say, wow, the light source is there. And furthermore, it's a 3-dimensional structure, so we can actually pull it out not only in 2D, but also in 3D. And then track it as it moves. And for the single light source, it's extremely precise. We have a fairly overdefined system, so we can get a pretty good signal to noise. And we actually get precisions, this is about 0.5 millimeter off the chip. We get precisions on the order of a 1/10 of a micron laterally and a micron per. Of course, this is not imaging, this is a single light source. But for that, it's pretty cool. Okay, so why is it not imaging? Well, this idea of thinking of incident angle is really only meaningful when you have one light source. If you have 2, then it loses all meaning. So what's the incident angle here? That's not a meaningful concept. So if it's not defined, what else can we do? Well, we can sort of do a back projection, a sort of first round inversion, by just noticing that if we have peaks in our responses, and certain pixels are responding strongly, then probably the light sources can be backtracked, being locations for the generators peaks. So we can sort of back project where the light is likely to be coming from and begin to develop a map of where our likely light sources are. And then we look at those correlate well with the actual ones. So now one thing you notice is that we don't actually care about the raw responses. What we care about is those differences, because we're really interested in the angular piece, and that's in the complementary sort of sine and cosine signals. So we'll be thinking about this sort of complementary waveform from here on out. One nice thing about this view is you can extract a resolution number on this and say, well, what is my resolution in this viewpoint? My resolution is basically proportional, or the smallest spot I can extract is proportional to how far away I am. That's not surprising. But inversely proportional to that term beta, that periodicity term. So if you make a higher frequency response, I'll get a better resolution. And that's true both for the XY dimension and also for the Z dimension. And the only modification on the Z is that we have an additional requirement. We're sort of triangulating, so the steeper the angle, the better the Z resolution. So we did this. We suspended little blobs of fluorescent beads above a chip and tried to reconstruct what they were. We get, for one clump, we see this. We can see a strong blob and a weak blob. The weak blob is basically a consequence of the periodicity of the system, so we're getting a little bit of ambiguity. It could be in either place. If you put 2 blobs in there, it fails. So, okay, so we're not there yet, but it does something. Now, one thing this math tells us is that our resolution is dependent on this term beta, so maybe we can make the beta larger. So we did that. This is a higher beta design. And that gives us a better resolution, but unfortunately also comes at the cost of worse ambiguity. There are more possible locations that would explain the place. And sure enough, if you throw again the same clumps of source and beads at this, you get a disaster. You get this just sea of ghosts, even one of which could be the agency. So that's no good. But there's sort of something in here. You can say, well, low betas gave me lousy resolution, but not too much ambiguity. High betas gave me better resolution, but lots of ambiguity. If I combine both, then in principle, I could basically overlay them, get good resolution on the spot, and at the same time eliminate most of my ambiguity points because they wouldn't be explainable. So we've done that. And you do this basically by just putting adjacent pixels of different types near each other. And when you do that, you get a significantly cleaner result. So we can actually isolate two distinct clusters of fluorescent beads at different locations just by combining with clusters. So the basic sense it works. This is still not a very big array, it's a 32 by 32 array of those tiles with two different betas. And it works very well. This is basically a pseudo inverse we're throwing right now. Now there's a problem here. You can formulate in general. Say, in the general case, what are we doing here? What we're doing is we're taking a planar array of fancy sensors, and we're trying to reconstruct a cubic, a volumetric array of possible light sources. So you can frame that basically as a piece of linear algebra and say the measured result y is just that volumetric set of sources x times some transform k. Now the problem here is that, of course, the dimensions of the volume are n cubed. The dimensions of the array are n squared, so this is not an invertible matrix. There's no formal general purpose inverter here at the board. This is a pretty much general problem for volumetric measurement without some form of scanning. We just don't have enough information. So one thing we can do about this is we can say, well, if we know that our sources are sparse, and often we do. So, for example, if we're looking at isolated fluorescent cells in a volume, there's not that many of them probably. In a number of other scenarios where that's true. If it is sparse in some basis set, then you can start throwing all these techniques that have been developed for compressive sensing methods. Basically say, instead of just simply inverting it, we'll actually try to minimize the mean square error, but regularize by the L1 norm. I won't go into it. This is lots of math there that I only have to understand. But if you throw this at the problem, you get a much, much better result. It really clarifies it. It basically does so because it just says, what's the fewest number of points, roughly, not quite those two, but close, that are sufficient to explain essentially all of our results. And when you do that for a reasonably sparse input, it works quite well. So that's the lensless version of what we're doing for 3D. What about with a lens? So in this context, we're going to think about it more in the kind of the general way people look at 3D photography, which is not really 3D. It's really more 2D problems. Because you're assuming opacity, you're not really seeing the full volume of things, you're just seeing the surface. In which case, you can basically think of it as a 2D map of intensity and a 2D map of depth. And that's, of course, a much more easily inverted problem than the general volumetric problem. In order to make this interesting, we need a bigger chip, so we built one. So this was manufactured in another standard manufacturing process. We designed it on a computer, we shipped it with a check to Taiwan, they shipped us back a bunch of chips. Off we went. Briefly, some random little specs. It's a multi-100 kilopixel camera or sensor. It's about as big as you can buy for reasonable money, and includes not just the optics but also various electronics, so multiplexing and all sorts of things that are easy to do in CMOS. We also took the diversity of pixel observation to heart. So now our tiles are significantly more complicated. We have 4 distinct betas with periodicities, 8 and 12, as well as 24 and 16. So that gives us both the low ambiguity, low resolution ones, and the higher ambiguity, high resolution ones. We also have more orientations. We have vertical and horizontal. We have diagonals now. And we also still have our 4 betas. So we end up with actually 64 distinct light sensors in the system, each with its own set of gratings. One little fun side thing we did is we said, well, to CMOS image sensor, we need to include local electronics. That's what we do in CMOS. So we use a standard 3 transistor pixel. Now we get the information out, but we have all these wires. They're called diffraction gratings. So we just use them as our buses as well. It's more fun than anything else. And so you can see the little tie downs where the wires go through. So now, how do we use this? So now, let's start with the simple case, which is when you're in focus. When you're in focus, your objects arrive at different locations spatially. the images of the objects rather, and angle is relatively ambiguous. It's coming from a wide range of angles. And so what the image sensor will see is essentially, for example, two spots at two locations. Because the angular information is basically washed out, each of these pixels essentially throws away the angular information and becomes a standard normal intensity pixel. And so your resolution ends up being just the resolution of your photo values, just like in a normal camera. So you do lose some light, a bit of light from the gratings, but in terms of sort of resolution, you're no worse off than you would be if there's no gratings at all. Same resolution. But as you move out of focus, now of course your spatial information becomes much worse. You get big blurred spots. So from that perspective, you're losing a lot of information. But at the same time as you do that, you're now mapping those spatial locations that are being blurred out to angle, not the pixel itself. So now you can see our two objects in space are showing these two different angles down that pixel. And that now means that, a little bit of math, I'll come back to this math later, but you can basically say that those locations are now mapping to different points on our angular response curve. So the blue object is going to excite actually a negative response in that pair of pixels. The red one is going to excite a positive one. So they're actually distinguishable from that. And more generally, if you look at this in the 2D sense, a given pair of complementary pixels will have a transfer function that looks something like this in angle, with a kind of periodicity and an orientation, with those two spots in space being weighted by these two different parts of the filter. However, because we're blurred out, we're not getting just one pixel, but a whole family. So we actually get a whole family of these filters, which looks like this. And one thing you'll sort of notice here now is we have a whole bunch of different representations of the same information, each of them being weighted differently. And furthermore, those different representations look a lot like a local Fourier transform. So if each of these were one coefficient from a 2D, it's not actually a Fourier transform, it's more like a Hartley transform, but a 2D local Hartley transform of an incoming angle. So why is that good? Well, 2D Fourier or Hartley, they're the same, pretty similar. Has some interesting implications. One thing it is it's a complete basis set is invertible. So we can back out the divisional spatial description. Another is that they're typically orthogonal, so not only are they invertible, but they're easily invertible. It's very, very easy to invert this kind of information. It's also well characterized for natural scenes. People spend a lot of time looking at natural scenes and running through this kind of transform and understanding what that means. And what we know is that it's a good transform. It tends to give you a sparse result that captures interesting information well. So it's not only true for our compression algorithms, but actually your visual cortex does exactly this kind of transform. And then finally, it gives us a nice mapping to other forms of light field imaging. So for example, to this sort of classic array pinhole approach, we can think of that approach as basically taking light from different angles and mapping them to different subpixels. For us, we're doing exactly the same thing, except instead of mapping subpixels, we're mapping it to Fourier transform that set of subpixels. So there's actually a one-to-one correspondence between our technique and other ones that are already out there. Okay, so this tells us overall that we have a couple of different sampling regimes. One sampling regime is the in-focus regime, where we basically just use the raw intensity or the sums of our ASPs, and we throw away the input information. We also have a different sampling regime when we get sufficiently out of focus, where now we're basically using the differences between the angles of pixels and extracting angular, sort of this Fourier transform of the angular distribution instead. And that's true both too close and too far. So now, as a sort of demonstration that this is true, we'll throw a kind of a classic light field demonstration at you, which is the computational refocus problem. And I have a little caveat at this point, which is there's been a lot of press lately about computational refocus, particularly coming out of Nitro. I don't know how many of you are keeping up with this. It's really cool, it's a really great demo. It's not, every photographer I've talked to is kind of like, really? I can do this. So, before you think that I'm of the Nitro camp, which are from Stanford and I'm from Berkeley, so close enough. Let me just say that the nice thing about computational refocus is it tells you how much information you have. The better you can computationally refocus from a defocused scene, the more information you know you have coded in there somewhere, but you're somehow able to get it back. So we can kind of take it with that grain of salt. So here's our initial setup. We're in focus, so that's just a raw intensity image. You can see our two words. Now we deliberately draw ourselves out of focus by just moving the lens. Now the intensity image is hard to read from. But we have a lot more information. So we have the raw intensity information, which is pretty coarse, but we also have all of these different differences that are angular sensitive. So here's example one. You can see there's clearly extra information here. Now remember, we actually have 64 of these, so we have 32 differences. So So we have effectively 32 sub-pictures being taken from each different type. And so you can see here now, all those different gratings are represented. We have different frequencies in our capture, the different betas. We have different orientations, there's diagonal and horizontal. And we have even different phases, so there's like the sine and the cosine. So there's a lot of information here. How do we use it? So we'll go back to that Fourier transform idea. Say, well, one thing we know about Fourier transforms and things like Fourier transforms is that they are their own inverse. So if I want to invert the optical processes that gave me these outputs, all I need to do is convolve these various signals with their own impulse functions. So for example, take the sort of the essentially first order set here, convolve them with this set of impulse functions and add them up. And I get back I'd argue, cleaner representation of the original signal than the raw intensity. I can do this for the higher beta ones, the higher harmonics, and I get another one but with interesting sort of gift effects going on. And then I combine them all together, and I get a much cleaner representation of the original signal than I had just in the raw intensity. So sure enough, it's there. It's not beautiful, but it's a lot more beautiful. Okay. And this works, so now we can sort of see what we mean by a regime. We have our in-focus regime with just intensity. And then as we move into the out-of-focus regime, we start to blur out an intensity, our intensity images, but we can get it back by using the angular information to get back into focus. And this doesn't mean that we have perfect focus everywhere. As I move farther out of focus, both my representations degrade, but the refocused version degrades a lot more slowly. And effectively, in this context, it gives us about a factor of 4 improvement in f-stop number for the same optics up front. So basically, this additional emissions increasing our depth of field by about a factor of 4. But with the additional benefit, that increase in depth of field is something we can control after the fact. So you can pick your subplane within that deeper depth of field on a post-processing basis. So just to convince you that it works on something other than little words, I took some dice. This was a suggestion of the graduate student in my group that is more interested in radios than imaging, and she doesn't believe in any of it. That's all we did, something in real life. So took some dice. Start off badly out of focus. You might conceivably be able to figure out what's going on with your dice. Maybe not. We kick in the computation refocus. We move our focal plane back a little bit. It's a little bit cleaner, a little bit cleaner. Now you can start counting all the pips in the back as well as the front plane here. You can focus all the way through to the rear die. So this is all after the fact computation, just based on the outputs of those differences in grades. So now the other half of the light field problem is now we have a better representation of intensity. Now let's do depth. So we'll start with a simple sort of demonstration, sort of three white bars at different depths in front of our same camera. Here's the intensity picture. I think if you squint long enough, you can convince yourself that these two are a little less focused than the middle one. But I challenge you to figure out which goes to the front. I don't see the information. However, if you now look at one of those, this is a vertically oriented one of those angles and pixels, you can see that each of those bars is being represented very differently. You can see that cleanly, you just take a cut through, and you see now that on the left they're all pretty similar. On the right, one of them goes plus and then minus, one of them basically does nothing, and the other one goes minus and then plus. So each of them is being represented very differently. So having we interpret this sort of intuitively, you could say, we know these responses here are being derived from an angular transfer function. We also happen to know that we have a finite aperture in the lens, so we're really only looking at this piece of it. And with that information, we can say, well, whenever I see a positive response down here, it corresponds to a positive angle on here. Like so. And whenever I see a negative response there, I know it comes from a negative angle. And so I can basically back out a local vector field just from the pluses and minuses. And furthermore, if I get no response when I know there's an object present, then I must be in focus because these two pluses are essentially canceling each other out. So interpretation-wise, I can now say, well, I have my three objects. I initially don't know how deep they are, but when I see a convergent pair of rays, I must be closer than the focal plane. If I see a divergent pair of rays, I must be farther away. And if I see essentially cancellation, then I must be in focus. So then I can basically back out a depth map from that. It roughly estimates where my three objects are. And this works not only on bars, but also on dice, left dice. I don't know why. So for example, here you could say, well, you can see that they're a little bit fuzzy. Is the focal plane in front of both of them? Is it between them? Is it behind them? And what you can find is actually, as you, once you do that range mapping, you find that in fact the focal plane is directly between them. You can actually get that depth of information out just by basically operating on the edges in the sequence. Now, we can be a little more sophisticated than that. We go back to our various nasty math. And the main point I want to get to here is, as you work through this math, you find that the final response, the voltage response, is an integral, but in that integral is a cosine function, for example, or a sinusoid function, and the depth, z, is actually inside the sinusoid function. So we have this is the input, this big mess, but the depth information is actually contained within the essential frequency response of our sinusoid. So we can use that by just approximating our two inputs, the sine and cosine, with that same coefficient inside, and then doing a little bit of trigonometry. And particularly, the trick is to notice that if you take the derivative of a sine or a cosine, the frequency comes out. So you take a spatial derivative, like basically taking the difference of adjacent pixels, and pull out that information. And then you can normalize everything else out just using simple trig. So the final outcome is just a depth number, a scaled depth number. And when you do that, you get this sort of map. You notice it's a little bit better. It's a little bit better noticing the front end of the dice is closer. It also notices that actually picks up in the background now. Notice the background is way far away. It also has some annoying artifacts that we're looking at. One of them is that for some reason, these little pips are actually lighting us close. What's that? Well, that is the fact that the pip is actually concave, and so the light that's hitting it is actually reflecting back as if it was close. So it's optically right. That's close. It's not actually. And similarly, you notice here that the background seems to be leading onto the top of the dice. Well, let's suspect the reflection of the background coming on. So we're reenacting onto the reflection. And this is actually shows up in pretty much any light field system you look at. You start getting these sort of strange artifacts that are really reflective artifacts that our brains clean out of our optical perception. So if you show yourself, if you look at yourself in the mirror with a light field imager, it'll range map yourself through the mirror. And the other thing I just want to point out here is that the math is actually quite simple. There's about 8 arithmetic operations here to get to a range number, which is a relatively efficient light field depth finder. There's some neat tricks making those better. Okay, so how else can I use this information beyond just the light field side? So one realization from a signal processing perspective, so what we're actually building here are a set of filters. So our raw intensity number is essentially a low-pass filter whose bandwidth is set by how out of focus you are. But our angle-sensitive pixels now are actually acting as bandpass filters, responding to particular center frequencies set by the periodicity and then bandwidth set by their envelope. And we're generating multiple of these. So we're generating a whole array, essentially, of bandpass filters on our CMOS. So how can we use that? So first thing to notice is that if we have a set of bandpass filters in angle at the imager, then through a lens that corresponds to a set of bandpass filters in space out in the real world. And what are bandpass filters meant for? Well, one thing they use for a lot is, in the context of image processing, is compression. And so, for example, here I'm taking a classic LEA image, I'm convolving a set of distinct 3D bandpass filters, and you can see it automatically pulls out sort of edges and so forth, but sends most of the picture to zero, to gray. So why is that useful? Well, if I compare the original histogram of pixels to the outcome of filters, you can see it's much more dense. And so if I were to round this off, most of my coefficients would round to zero, which gives me a much better compression. You should also note that this goes beyond compression. It's just generally said that once I do this transform, I can operate on a much smaller number of pixels and still get all my information, because most of my pixels are going to zero. And the one key to make this general is I have to fill out my filter grid. I have to basically map or tile frequency space up to some frequency well enough that I have all the information there when I want to do reconstruction. So we can do that. So we start off with a tile on a newer design. We have actually 48 distinct pixels, so 24 pairs. These are actually pairs of pixels now, pairs of photographs now. And each different sets of them correspond to different frequencies. So we have a low frequency bunch that fills out one part of the frequency space. We have a high frequency bunch that fills out another part of the frequency space, and then we designed a medium frequency set to basically fill in the gaps. So now we have a reasonably complete map of a frequency space in angle and therefore in space. And this is all measured results. These are measured impulse responses. So now, just as a demonstration, this actually could work as a compression algorithm and more generally capturing useful information. We start with, first of all, just to know what we're working on, we take a picture of a picture. In this case, this is what it looks like in focus. So we're just running straight intensity numbers off of it. If we put that out of focus and capture our angular information, we get 24 subpictures that look like this. And you'll notice here, we call that the rounding operation. And you'll notice now that the various edges are still represented, but now all the background stuff is raised at 0. So we get a big sparsification of our information. We combine this back together to do reconstruction. We can get back essentially all the edge information from the original scene, though the intensity is still not there. And then if we combine it with the intensity information, but subsampled by a significant factor, it's blur. So we can downsample that by a factor of, I believe, 24 in this case. And we combine, we get back something very close to the original image, but now compressed down by about a factor of 10. Now that's not a great compression algorithm. 10 is not a great compression factor. But notice that all the hard math got done optically for free. And the rounding is called for analog digital divert, which you have to do anyway. So you actually end up with potentially a system where the imager consumes less power than would otherwise. But it's doing compression one way for free. So it's cool at least, right? Whether it's useful, we can argue about. I think we're sort of moving in the direction of how do we combine this with 3D to get a compressive 3D imager, and then that's pretty cool. All right, what else can we do? I'm almost done. One more thing we can do is we can say, well, let's just get rid of the lens. Let's go back to no lens. But now what we're going to try to work on is the far field. And so what we'll do is we'll basically say, we just saw we can do reconstructions based on this sort of Fourier transform idea. So we'll just make the biggest Fourier transform we can. We'll just plunk down every grading pair that'll give us a Fourier coefficient we can come up with. We'll actually do an overcomplete set, and we'll just basically fill out a chip with that. So this chip here is, scale on here. It's about a millimeter by half a millimeter. It has, there's just sort of 2 sets of complementary ones. It has many different ones as we can, so we've got about a couple thousand sensors. They're a bit overcomplete, so we have about 400 independent readings. And this is actually an invertible set of data. And if we invert, we basically get back a picture. So for example, so what we end up with is basically taking pictures of the Fourier domain, and if we invert it back, we get a very small, very bad camera. And the only defense of it being very bad is that it's incredibly small, both physically in 2D, but also without a lens. So how does that work? Well, so take a picture of an edge, we can reconstruct an edge. Take a picture of a spot, we can reconstruct a spot. Take a picture of great art, and we get back something that most people recognize as a face. So I wouldn't be using this to take pictures for my family vacation by any means, but it's kind of an interesting space. It sits somewhere between small cameras and photodiodes. It potentially opens up a sort of a sensory space where you're not really interested in the Mona Lisa, but maybe you're interested in the location of an edge or the motion of an edge, some sort of low resolution visual information. And then potentially this gives you a sensor that costs a penny, that gives you this capability. And since it's in standard CMOS, you can include processing on board and get a complete system that spits out, motion information just directly with no active illumination at essentially no cost. All right, so before I stop, I just want to spend a little bit of time on sort of our second pass on angle principles. So I suspect most of the people in the room have noticed there's a big problem here. The big problem is that we have a lot of metal over our diodes, so we're losing a lot of light. In fact, each grading is blocking between sort of 60 to 70% of the light at least. Ideally, it'd be 50 because they're 50% duty cycle, but we're approaching the diffraction limits here. It's actually worse. So that means that the overall quantum efficiency is being reduced by somewhere between a factor of 6 and a factor of 10, depending on the configuration of gradings. And that's pretty awesome. So what can we do about that? So we've tried 2 things. The first thing we've done is try to remove the second grading, analyzer grading, by removing the photodiode and replacing it with a bunch of very fine-grained linear photodiodes in their place. So this gives us one nice thing, which we actually get both the plus and minus versions of the signal in the same pixel. In principle, we get more light because we're not blocking it from metal, but it doesn't work as well as we might hope, because I might hope. Because now our diodes are much sharper because they're much finer resolution. So the result is a lot more photons just go right through them, essentially flutter out. So you get an improvement in quantum efficiency, but it's effectively, it's not the full sort of factor 3 improvement you're hoping for. It's more about like 1.5 in terms of the information you care about, because so much of it is being lost through. But there you can see that our nice ASP response doesn't work. Second idea is to try to get rid of the top grading. And so the way we did this was we took existing structures and we just did it with basically one crude mask to protect our bond pads so we could get information out later. And after that, we do a simple non-peak reactive ion etch, so an anisotropic etch on the oxide, which chews down past the top grading, as shown here. Then we strip off the metal, and we get what's now phase grading instead of an amplitude grading. And so note, this is basically very low cost post-processing on CMOS. We're not going to do any fine grain masks. We just put it in 2 machines and we're done. So what's the nice thing about phase grading is they generate the Talbot effect just like an amplitude grading. So we get the same, these are simulation results with the same angle selectivity, but now without any loss at the surface. So we've built those two. They give us the nice curves. And the next step, which we've half done, is to build an image reference. We have the chip back. We have the manufacturing process. We haven't actually done steps. So hopefully in a year or two, hopefully in 6 months, we'll be able to present a much higher on efficiency 3D imager. So with that, I'll stop. So in summary, we've built pixels that are sensitive to incident angle and intensity. We've built arrays that are capable of capturing 3D image information, both in the volumetric sense, but also in the sort of more classic light field camera sense, with our ranging and refocus. And we've got information that's in a format that's useful for other forms of image processing, both for the sort of compression style lens imaging, but also for purely lensless imaging for very, very small cameras. And the nice thing is all of this is done in the context of a standard CMOS manufacturing flow. So we basically opened up another component that circuit designers can just plunk down on their chips next to their microprocessors and their radios and all that. So with that, I need to acknowledge both the people who did the work. So Albert Wong, he's now at Apple, but he was the sort of leading light on this. He's a physical chemist, so Patrick Gill, who's actually a neuroscientist before he did this. Sriram, who's been doing the new ASPs. Various other members of the group who've done all sorts of other things, and the various agencies that support it. Thank you.
Is it true that as you change the beta periodicity, you have to change the depth of the grading, and how many different depths can you accommodate?
That's a good question.
So and also wavelength.
Yes, both good questions. Okay, so to the first question, there are 2 ways of changing beta. One is to simultaneously change the pitch and the depth, and so that just gives you a different Talbot depth when you go from that. The other way to do it is to hit a different multiple Talbot depth. So you can hit, the first one or the second one, and then you can do that by either just changing pitch or just changing depth. So we've done both. Typically, so the process we were working in, there were 55 good metal layers for this. So we had not 5 choices because the pairs are the same, but there's some common torques there. A lot of choices of metal layer combinations, and so we ended up picking, a few that were good. So there's some constraints in this. This actually doesn't work very well if you don't have at least about 5 metal layers to give yourself enough freedom. And then wavelength. Yes, wavelength is an issue because the Talbot effect is wavelength dependent. I might even have a backup slide. Yes, here we go. So I'll just jump to it on top. So this is the sweat pitch. These are sweat pitch. We measured the modulation depth, so sort of how good the curves are in the beta for green light. And then we did for blue light 2 back. For blue light 2. What we basically see, so what you can see is things shift a bit, and the optimal designs shift a bit because the Talbot depths shift between green and blue. But there's actually a design space in here that covers both reasonably well. So we found in general, as far as we typically use low order Talbot depths, either the first half order or the first order. For that, we can get a single pixel to cover kind of blue through orange, if you will, with reasonable performance, and red just the size. And so all the pictures I showed you were actually with white light. And the reason that works is that the photodiodes are also a bit green optimized. They're N-wells, they're out of micron deep, so they do best with green light. So we show them white, and they basically are responding to sort of cyan or yellow effectively, and it works pretty well. But this is a weakness of the design. So one thing we're looking at now is actually combining this with a more standard CMOS image sensor process that has color filters. So then you can co-design your angle specific pixel with a band, and then we should be fine.
So you can get a greater depth of field with a higher F number system as well.
Yes.
So I'm just wondering what you really gain by doing this. It seems like you don't get something for nothing. In particular, in your focal plane array, you can't ultimately get the spatial resolution that you could before because you've got to cover multiple angles.
That's right. So, so there's a couple things to say there. One is that if all you want is depth of field, I don't recommend doing this. I recommend getting it. That's why that was my little song that's thinking that computationally focus is a little bit bogus. Nah, that's what. I will say that actually for the effective depth of field we're actually getting more light than having an actor. Because although the gratings block a lot, the effective depth of field is about f8. And if we starting out with about an f2, and if you did the factor 4 reduction, you lose 15, 16 of light. Here we only lose 10. You make it come out ahead. So there's a conceivably an argument to make there, particularly when you use a phase gradient, so you big help. So you might be more sensitive to the same f-stop, maybe. But I think the real thing you win is the depth finding aspect, because that's something you can't. It's not so easy to do with just a f-stop. So that is the real thing.
I'm trying to compare with other depth ranging
Yeah.
and information and imaging. They normally use 2 images, so here we are taking effectively multiplied by 16 or 12.
Yeah.
So how does the signal to noise compare? Because you're spreading your light. So you need 2 matrices at the end and you're taking 16.
Well, so I would argue that this classic 2-camera approach has some sort of annoying holes in it. One of them is to take your classic binocular camera and you do this, and suddenly your processing is a lot harder, or at least it's different. So there are things that a simple 2-camera system will mix in this. Of course, put a 3rd camera in there, and you've got everything. I would argue that in this context, the win here is not necessarily in fundamental capability, but in cost. So it's 1 lens, it's all integrated on a chip. So I think in that sense you come out ahead. And the computational cost for getting range is pretty low. And usually you look at least a lot of these depth finding algorithms. A lot of them they'll do is the first thing they do is they Fourier transform the 2 scenes and they do organic. And we use the Fourier transform in the optics, so we kind of come out ahead that way. So if you wanted to build a really low power, low cost range finding camera, potentially we come out ahead because we could put it on chip and have a whole system. But they do map to each other, and I honestly am still trying to come up with the right metric. Actually talking today helped me with that. The right metric for comparing these different systems that gets us beyond just having a mapping, but an actual like one-to-one comparison of which is better. And so I don't actually do answer for that question.
So for your depth finding, you took your angular transfer function and you essentially windowed it so you only had 1 period of that to give yourself.
That was the intuitive version.
Okay. So I guess my question is the field of view of your system, does that have to be co-designed with your transfer function for you to remove that ambiguity, or is that?
So I think it's a good question. Ideally, it would be co-designed. That's your best bet. As long as you have a sort of sufficiently diverse set of angles and pixels, you're not too sensitive to your window because they give you enough information. But yeah, the ideal design, I was talking about the bandpass filters. The width of those bandpass filters is set by that envelope, and the envelope is probably set by your aperture. So if you could co-design the aperture, you'll end up with a cleaner set of filters.
So I'm trying to figure the pitches involved in the gratings, and it strikes me that these processes, these pitches were reasonably compatible with things and sort of heteroization. I was curious about how much trouble you had with sidewalls of the gratings.
That's a good question. So they are. The sidewalls are they're a little bit they're thinner than they are wide, but not a whole lot.
Not a whole lot.
Yeah. So honestly, I don't know. They work, and we didn't do anything about it.
I mean, they're not super reflective for those reasons.
No.
So that probably helps a lot.
Yeah. And one thing is the surfaces are polished typically, but the sidewalls are not.
Right.
So I think as far as we can tell, because we're using low order Talbot depths, and we're not too far, the slight ripples and stuff won't matter because they're way subwavelength. So the main thing that we think matters there in terms of sidewalls is essentially what effect it has on the effective width to gaps. And that's the effect upon efficiencies and things. So we always aim for 50%, it seems like the sweet spot. The reality is probably not quite. And I think the sidewalls are tilted a little bit. So it'll have that effect, but we haven't seen even any reason to believe it's having a big effect. We actually simulated some of this stuff too. It didn't really matter.
Okay, so I think it was slide 63 where you're showing kind of sample frequency space and that corresponded to little sections of the chip.
This one?
wondering, was there a reason the chip was laid out the way it was?
That's a great question. And there's a good answer to that. Or not
That
this
one,
second.
yeah.
This one. Okay, yes. So it's random. It's random for two reasons. First, the starting point reason that I was dramatically opposed to was that about the time we were designing this chip, both the PhD student and the postdoc involved got obsessed with compressed sensing. And they're like, random. And they were really pushing for random. And I was dead set opposed to being an old school engineer. So then we did a whole bunch of simulations. And turned out random was better. From a kind of a, what we basically did was we tried different arrangements of them. We simulated them with different sort of scene statistics. And we kind of asked how much information we would get out from different focal degrees of defocus. And what we found was that sort of empirically, the amount of information we got out whenever we tried to design it well was less than when we didn't try to design it well. So we just kind of went random. I'm a little bit regretting that now because it turns out for certain sampling conditions, we probably should impose a few rules on ourselves that next time we go, particularly in terms of getting the sort of sine and cosine versions of things near each other. Because if they're offset, then they're not really sine and cosine or something else. So that's, I think that would, next time around, which will be soon, we'll get those aligned with each other. But yeah, it's deliberately random, and that was kind of a choice.
Your Gabor wavelets are all raised because of negative values.
Yes.
So
This is why we always have complementary sets, because we need the pair to get negative values. Right. So actually, I did talk about it. Something that's fun here. There's actually 4 photographs in here, in the common center of the arrangement. So we'll have like 0 degrees and 180 degrees, or 90 to 70 for these. And so they're intense. There's no gradient dependency there. There's just a raw angular stuff. But yeah, you have to have a pair. You can't do that.
So CMOS is quite fast. How quickly do you scan the chip? And is it possible to oscillate the out of focus thing mechanically so you can gather additional information?
Good question. So the speed of this is ultimately not limited by the circuitry on chip. The circuitry on chip can go a gigahertz clock rate and the problem is getting enough photons, so you have your reasonable speed of noise, and then getting the data off. Because you're streaming out at least 8-bit numbers. If you have a gigahertz clock rate, you're streaming out 8 gigabits per second. That is in principle dealable with. People do it all the time, but it's not trivial. And getting a computer to absorb all that data in real time. So we've so far not been limited really by the electronics, but by the available light and the data acquisition system after. Which is actually one of the reasons why this concept of being able to do some form of either compression or on-chip processing is attractive, because it implies we could get a pretty wide field of view, get useful information, but not just beam all data off. So do a little bit of local selection on that. As to the fluctuating the lens, we've given that a little bit of thought. We haven't done anything with it. In principle, as fast as we can get the data off, we can do whatever we want, as long as there's enough light.
One more question if I can. Is there a singular advantage over this compared to an array of lensless?
Right.
And using, for example, a number of pixels within each square area there.
That's a very good question. So I'm going to give a nuanced response. So compared to taking a tile this size, putting a micro lens over it and using something, this is better, at least in some cases. And it's worse from an efficiency perspective that we're working on, but it's better in the sense that the lens delivery rate does not do well when you're in focus. It has basically 2 sweet spots, which are when the blur is on the scale of the micro lens, either one way or the other, just like we do. Whereas we have an additional sweet spot, which is when we're in focus, which they don't have. And on top of that, one thing we're looking at now is to actually, we have a non-uniform sampling of the different betas. We can actually get more sweet spots. We haven't done this yet, but the math looks great. So we have potentially an ability to sort of have a wider range of degrees of defocus where we still do really well in sampling, which the lens people can't. Conversely, now the nuanced response. Our pixels have to be a certain size to get enough periods of gradient, and they don't have that problem. So they can potentially make their lenses smaller than we can make our tiles. So that's the nuance. I did that.
Okay, if there are no more questions, let's Thank you again.